2m, right? That's the square root of 2m and the square root of energy minus potential energy. So this is total energy minus potential. That's all momentum. You do the integral, you get this out of the integral. And the action has to satisfy a certain constraint because of reasons that we will not discuss. So that if you're given a certain value for the total energy, okay, you can find where the correct value of R, for which this is 0, which give you RA and RB, and then you can do the integral, right? So you get a number, and you can compare that number to this, or you can put this on the other side and compare the subtraction of these two things to 0, okay? And now it's a root finding problem again. So given an energy, you root find to find RA and RB, and then you integrate and you minus this thing, and then you find that's your function that you want to define the root of. It's a function of the energy you put in, okay? So that's now you've kind of combined root finding, integration, and root finding in a intricate pattern, if you will. The problem is easier if you remove the units, so that's what they did here. And then you just have this gamma parameter, which represents the level of quantum mechanical effects. For H2, so 2 hydrogen atoms in a molecule, gamma is 21.7, and for dioxide, so 2 oxygens, gamma is 150, so it's much bigger. Okay, let's just keep analyzing the problem again. See what we have to do. Alright, so there's a function that takes E, okay, does stuff, and returns the action minus some blah blah and blah blah, okay, and we have to find the root of that function. Okay, but the first thing you have to do, so E, okay, you do stuff, more stuff, then you integrate well, the momentum from RA to RB. Okay, that's one level down. That's part of this, right? And then minus, okay. And then if you go all the way down, you see that you have a function, base E, and then here you have a function that takes r, right, and computes e minus v of r, okay, and so find root of this function. Okay, actually there are two. Find roots of this function, right? Then call them RA and RB, right? Then integrate momentum from RA to RB. And basically you have to find roots of s minus n plus 1/2 or something, right? Then you have to find the roots of that. You have to find the roots of the integral for which you need to find the roots of this function. And the flow of information is you start with e, then given e, first thing you have to do is you have to find the roots of this function. Then you have to integrate using these roots to find the action. You have to compute this. That's one computation of this big function. But you have to find the roots of this function, so you have to feed it different e's and do all kinds of things we do. Alright. So that's the plan. And as much as I am eager to try it out, right? From what I've already described in the numerical method section, you should be able to solve this problem by yourself. So before I go through and actually try to solve it myself live, I'm going to take a break, leave that for tomorrow, and you can take a break, and before you watch the next video, you can try to solve it yourself. You can try, sit down and put the things we have made together. It's probably not going to be pretty, and hopefully I can show you a few tricks to make it a little less, a little more obvious what the structure of the problem is, and to avoid too much copy pasting. But copy pasting is fine in the beginning, so that as long as you understand what you're doing. And yeah. So once you build the framework to find the roots of the function that integrates with the boundaries being the roots of another function, right? Once you can compute that, then you have to find all of the energy levels for different values of the quantum parameter gamma. So you have this function and you can fiddle around and see what happens. Try to get a bit of understanding of the physics. If you're kind of lost or you don't know how to put the things we've done already together to make this, well, just try it. If it doesn't work, don't sweat it too much. We'll go through next time. Alright. Thank you very much. See you next time.